There are many ways we could start talking about the singular value decomposition. I like to start talking using the geometric picture as I think it is the most intuitive pictures of all of them. Remember the eigen decomposition of symmetric matrices? We saw that for any symmetric matrix A can be decomposed to be equal to Q multiplied by D multiplied by Q transpose, where those are the eigenvectors, those are the eigenvalues, and those are the eigenvectors matrix transposed. We had some geometric interpretation for this matrix before. This interpretation was as follows. If we had some normalized data points in a circle like that, then after we multiply by this matrix, right here, we will get an ellipse, and the direction of the maximum spread or maximum elongation for this ellipse is actually the direction of the eigenvector of the matrix A that has the largest eigenvalue. We have also seen that if this direction was called y1, this direction was called y2, then the corresponding directions in the original space x1 and x2 were parallel to y1 and y2. So this is x2 such that ax1 is equal to y1 and ax2 is equal to y2. We have also seen that since this matrix is a symmetric matrix, then those vectors right here, those eigenvectors, are perpendicular to each other. Also, we have shown why those corresponding vectors here in the original space also are perpendicular to each other, because those are the eigenvectors of this matrix right here, and if you multiply this matrix by all the data points on the circle itself, then you will multiply this matrix by its eigenvector, and since ax1 is equal to lambda 1 x1, then the direction of x1 will be the same as the direction of y1, and the same happens for x2 and y2. Then we interpreted this decomposition right here as having some rotation matrix, then some scaling matrix, and then some inverse rotation matrix. So to reach this result right here from the original data points right here, we first do some rotation in the clockwise direction like that until x1 becomes this axis and x2 becomes this axis, and after that we perform some scaling in the x1 and x2 direction by the amounts of the eigenvalues. So this is lambda 1, the largest eigenvalue, and this right here is equal to lambda 2, and then we do the reverse rotation in the counterclockwise direction to have the same angle theta here as the same angle theta right here. So this was the geometric interpretation of the eigen decomposition of symmetric matrices. Now rises another question. What if our matrix right here was not symmetric? In this case, there is no guarantee that this vector right here is an eigenvector for this matrix A. Also, there is no guarantee that the eigenvectors are perpendicular to each other. In fact, we will have the following situation if the matrix A was not symmetric. So A, non-symmetric right now. For this case, if we have our sphere here again, just like that, and we draw our circle in 2D or sphere in higher dimensions, and we have those points x1, x2, x3, and so on inside one matrix X. So here we have x1, x2, up to xn. Then we multiply this matrix by the matrix A. Then again, this sphere will be transformed into an ellipse like that. But the difference here is that this direction right here is not an eigenvector for the matrix A. So this is y1 again, and this is y2, but those right now are not the eigenvectors of the matrix A. In fact, we have seen from the BCA videos that those vectors right here are the eigenvectors of the covariance matrix of the data after the transformation, which are in general different from the eigenvectors of the transformation matrix A. Now, since those are not eigenvectors of our original matrix A, we can't guarantee that the original vectors x1 and x2, such that axi is equal to yi, we can't guarantee that x1 and x2 are in the same directions as y1 and y2. So actually, x1 might be in this direction, so this might be x1, and this might be, let's say, x2. In fact, we can't even say that those two vectors will be perpendicular to each other without proof. I will prove to you that those vectors x1 and x2 must be perpendicular to each other, but without this proof I'll be giving you, you couldn't have been quite sure that those vectors x1 and x2 will be perpendicular to each other if y1 and y2 are perpendicular to each other. And that's because a general matrix A can distort the scaling and can change the angles between vectors. Right? That's because a general matrix A can have a general rotation component and a general scaling component. And especially if the scaling component is non-uniform, the angles will not be preserved. Suppose, for example, you have two vectors here and here. So you have this vector right here, and this vector right here. And the angle here, let's say, is 45 degrees. If you multiply those two vectors by a scaling matrix where you have 100 here and 1 here, and you have 0 here and 0 here, then after the transformation, this right here will be much longer in this direction, while for this vector you will scale the x component by 100 and will not change the y component at all. So actually this vector will lie on this line, so it will be somewhere here, for example. Assuming, of course, that this is 100 right here, then the angle between the new vectors is less than 45. It is not 45 anymore, so in general, matrix transformations do not preserve angles. However, I am telling you that for this specific case, if those are the eigenvectors of the covariance matrix, then the original vectors right here will be perpendicular to each other. I will prove this fact later, but in the next video I will derive the singular value decomposition using this geometric picture.